Hello, Paul Watts here, High Flying Physics, supporting students getting top grades at A-level physics. This is the third video in a mini series on equilibrium. Let's have a look at it. So we've got a uniform hinged trapdoor of mass 15 kilograms and length 1 meter. It's opened by a force P at an angle of 40 degrees to the horizontal. The centre of mass of the trapdoor acts at a distance of 0.7 from the hinge. And you've got to calculate the value of the force P, and you've then got to calculate the force on the hinge and its direction. So there's our force diagram of the information we've been given in the question. Now, there are a couple of approaches we could take with this question. First of all, we know it's in equilibrium. We're going to be taking moments. Now, one way of taking moments is that you work out the perpendicular distance to each of the forces, and you work out the moments that way. An alternative way, which I'm going to use, which I think is a bit easier for this question, is you work out the perpendicular components of the given forces, and you work out the moments that way, as I'm going to explain now. We've got a force P which is acting at 40 degrees. And we know that the vertical component of P is P sine 40. If you've got any problems with working out perpendicular components, I've actually got a separate video which looks exclusively at just working out perpendicular components from a given force. And it's probably a good idea for you to go back and have a look at that. So I'm going to assume that you're happy with knowing that the vertical component of P is P sine 40. Likewise, the horizontal component of P is P cos 40, and likewise with our hinge we've got H sine theta, and then the horizontal component of our hinge force is H cos theta. And you know one of the conditions of equilibrium is that we can take moments about any point. In other words, the clockwise moments is going to equal the anti-clockwise moments. Now we're going to take moments about the hinge. As you know, we can take moments about any particular point. The clockwise moments are going to equal the anti-clockwise moments. But we've got to choose our point wisely. And as I've explained in previous videos, we always choose to take moments about a point where we've got the most unknown forces acting. If we take moments about the hinge, we don't know anything about the hinge force. We don't know the magnitude of the force H, and we certainly don't know its direction. So it's a really good idea to take moments about the hinge, because then nothing to do with those hinge forces are going to appear in our equation. So the clockwise moments about the hinge, so we have got the force which is making that trapdoor move in a clockwise direction is the weight, 147 newtons, and the distance there is 0.7 meters. And the anti-clockwise moments is provided by the vertical component of the P force, which is P sine 40, and we know the perpendicular distance there is 1 meter from the hinge. So that's P sine 40 times 1. And reorganizing that, we'll find that the P is equal to 160 newtons. Okay, the second condition for equilibrium is that the forces in any particular direction will balance. So in this situation, we can say all the forces acting upwards are equal all the forces acting downwards. Well, the forces acting upwards, we've got H sine theta, and we've got P sine 40. They're both acting upwards, and the only force acting downwards in that situation is the force of weight, which is 147 newtons. We're going to reorganize that equation to get H sine theta by itself, and we're going to call that equation 1. Also, because it's in equilibrium, we can say the forces to the right are going to equal the forces to the left. Forces to the right is H cos theta, and that's going to equal the forces to the left, which is P cos 40. If we now take equation 1 and divide it by equation 2, we end up with this arrangement. So H sine theta over H cos theta is 147 minus p sine 40 divided by p cos 40. Now, you can see there that the h's will cancel. You can also see that sine theta divided by cos theta, well, that's exactly the same as tan theta. So simplifying this expression, we are left with tan theta is equal to 147 minus 160 sine 40, substituting for our 160 for our p force there, divided by our p force, 160, times cos 40. Now, putting that into a calculator, theta comes out to be 19.7 degrees. Now, we haven't finished, because what we've got to do is we've got to work out the size of the H force. Well, because we now know the angle theta and we know our P force, we can substitute into any one of these equations to work out H. So let's take equation 2. We could take equation 1, but I'm taking equation 2 for no particular reason. And we substitute our known values in and reorganize the equation. So you can see there we've got H is equal to 160 cos 40. That's that expression there, P cos 40. So 160 times cos 40 divided by our cos theta, which is our cos 19.7, and that comes out to be 130 newtons. Great. I hope you found that useful. Thanks. Bye.